Hello, I am Zachary Adams, a rising senior at Georgia Tech majoring in material science and engineering. As part of the summer 2020 online O-REU at Texas A&M University, I have worked on the project Modeling Elastodiffusion of Point Defects Around Crack Tip Stress Fields. I'd like to take a moment to thank the Center for Research Excellence on Dynamically Deformed Solids for sponsoring this project, as well as Dr. Demkovich and ZACHARY Mao for assisting me. Materials in nuclear reactors are subjected to incredibly extreme environments, with high temperatures, corrosion, and intense radiation. The most damaging radiation for material is in the form of neutrons, which move through materials with incredible speed. When these neutrons strike an atom in a crystal lattice, their kinetic energy knocks the atoms off the lattice sites. Most of these atoms are able to return to their sites, but this restoration is not always perfect. Sometimes, two atoms may end up sharing a lattice site, forming a dumbbell-like structure called a self-interstitial atom, or SIA. The inverse of this is that sometimes there may be lattice sites without any atoms on them at all. This is called a vacancy. These material defects, called point defects, are formed together in equal numbers due to high-energy radiation. The presence and accumulation of these defects can cause many phenomena in the material, such as changing dimensions or degraded mechanical performance. These point defects are not static in the material, nor are they the only type of defect likely to be present. Cracks are such a defect and are inherently present in materials due to forming or mechanical loading. Cracks are three-dimensional defects that can grow throughout a material and can cause the material to fracture well before it yields. Around a crack, stresses from mechanical loading are amplified, tending towards infinite stress at the crack tips. The nature of the stress field around the crack is dependent on the loading mode of the crack. The simplest case, where the crack is being opened, is called Mode 1 loading. Mode 2 involves pushing on the crack face, and Mode 3 involves tearing the crack. The stress field produced by a crack is important as it can cause parts of the material to deform in different ways, or anisotropically. For point defects such as the SIAs and vacancies, this anisotropic deformation could make certain migration directions more favorable. Therefore, the diffusion of the point defects is likely to be affected by the intense stress fields present in crack tips. If we want to understand exactly how the diffusion of these point defects is affected by crack tip stress fields, we need a model for diffusion that takes these stress fields into account. One of the simplest models for diffusion is based on Fick's second law, which is very useful for analyzing most cases of mass transport. In this case, this model is inadequate as it does not account for stress field interactions of the migrating species. Fortunately, previous work has investigated the effects of elastic stress on diffusion, which is termed elastodiffusion. This work has investigated how the stress fields around interfaces and symmetric tilt grain boundaries affect the diffusion of copper atoms, and has developed a model for this diffusion process. This model, however, has not yet been used to describe the diffusion of point defects around crack tips. To this end, my goal this summer was to implement this model in order to understand how the stress fields around a crack tip affect the diffusion of self-interstitial atoms and vacancies. In this project, we will be using copper, which is a face-centered cubic material. The model for elastodiffusion is similar in many ways to the regular model for diffusion. Both involve solving a partial differential equation to get the concentration profile. In the elastodiffusion model, however, a tensor is used to represent diffusivity throughout the material. This allows for the model to account for different diffusivities in different directions in the material, as well as accounting for these diffusivity values varying throughout the material itself. The elastodiffusion tensor is a function of two main variables: the stress field around the crack tip and all the migration paths possible for the defect. To obtain the concentration profile of defects around the crack tip, there are many steps of calculation required. The first step is to choose the loading mode. In this example, we will be using Mode 1 loading. With the loading mode chosen, the stress field around the crack tip can be calculated using the exact equations for the stress derived from fracture mechanics. This image shows one component of the stress, the XY component, which has a maximum magnitude of about 50 pascals, which is very low. The normal components, the XX and YY components, have maximum magnitudes around 50 megapascals. We now take a detour to choose the type of defect diffusion we will analyze. In the current model, we can only solve for the diffusion of one type of defect at a time. For this example, we will choose self-interstitial atoms. Now, we must analyze the possible migration paths for the SIAs through the material. Now, for a regular atom, there are a total of 12 migration paths. This is the case for vacancies. For self-interstitial atoms, the dumbbell shape makes migration more difficult. For one, there are three possible orientations for these structures, with the axis pointing in the 001, 010, and 100 directions. And two, due to the dumbbell structure, the dumbbell can only migrate in a certain direction that is much more restrictive. Due to this, there are a total of 24 migration paths for the SIAs, 8 for each orientation. With that finished, the interaction energy can be calculated. The energy is a scalar value, and its calculation uses all the components of the strain. the interaction energy is only significant close to the crack tips, with a maximally negative value of 0.4 electron volts. The interaction energy is fed into the calculation for the Elastodiffusion tensor, and along with the vectors for each possible migration path, the value of the tensor is calculated across the solution domain. With the Elastodiffusion tensor finally calculated, the partial differential equation can be solved. The solution domain can be seen here. The outer edges have the boundary conditions of zero flux, and the crack surface has a boundary condition of zero concentration. The total crack length is 20% of the side length, and this crack is idealized with a thickness of 0. The partial differential equation was solved using a central finite difference method and a grid size of 501 by 501. The final solution for the concentration of self-interstitial atoms using the Elastodiffusion model can be seen here. The concentration profiles for both SIA and vacancy diffusion under mode 1 loading can be seen here. The shape for both are nearly identical, but the vacancies have a much higher equilibrium concentration, which is due to the much lower diffusivity of vacancies. To better visualize these results, the concentration profiles were normalized to a solution of the problem that did not use elastic effects from the crack. With this done, there is a slight relative change in concentration around the crack tips, but this difference is very small. The concentration profiles for Mode 2 look nearly identical to the ones for Mode 1 loading. The differences can only be seen when the elastic interaction profiles are normalized to the profiles without elastic interactions. Once this is done, it can be seen that there is relatively higher concentrations on the top right and bottom left sides of the crack, and relatively lower concentrations on the bottom right and top left sides of the crack in the case of SIA diffusion. This anisotropy is not observed under Mode 1 loading. To better understand what is happening at and around the crack, I analyzed the flux of defects around the crack surface. Using a rectangular contour centered at the crack's origin, I found the dot product of the flux with the normal vector of the contour. The next slides feature graphs of the fluxes along the lengths of the contour for parallel sides, that is, the top and bottom sides or the left and right sides. This numerical approach allows us to quantitatively see what is happening around the crack. These two graphs show the varying of the fluxes over the lengths of the contour in SIA diffusion. For Mode 1, it can be seen that the flux is higher due to elastic interaction, but the fluxes between parallel sides, for example the top and bottom, are nearly identical. For Mode 2 loading, this is not the case. There is a slight difference between the parallel sides, although the magnitude is not affected by the elastic interactions. A similar trend can be observed for vacancy diffusion, with the notable differences being in Mode 1 loading. Due to the elastic interactions, the magnitude of the flux decreases, instead of the increase observed in SIA diffusion. These graphs show the differences in fluxes between the parallel sides for all diffusion and loading cases. In both graphs, it is apparent that there is only a difference in these fluxes under Mode 2 loading. Here, a positive value for this difference indicates a preference for the top or the right side. A negative value indicates a preference for the left or bottom side. It follows from this that certain corners of the contour have relatively higher fluxes of defects entering, in both SIA and vacancy diffusion. This is only observed in Mode 2 loading. As a result of some corners having relatively higher fluxes of defects under Mode 2 loading, a crack under Mode 2 loading that is subjected to intense radiation is likely to rotate. Under radiation, this would mean that a Mode 2 crack is unstable, and is likely to rotate until it is completely under Mode 1 loading, which is a stable conformation. This motion is a result of the anisotropy from Mode 2 loading and is entirely unique to this loading condition. Now, with all the work that has been successfully accomplished this summer, there are only a few tasks remaining to be finished. The first of which is to solve for diffusion under Mode 3 loading, which has not yet been done due to time constraints. Finally, the partial differential equations for SIA and vacancy diffusion need to be solved simultaneously to fully understand their diffusion. Thank you very much for watching.